this, and now?
Yes, and now you click like this, and then you just share the screen that you will be.
And where is my keynote? I'm looking for a keynote.
Very strange.
Yeah, why don't I see that?
The preview. Try the big one on the left.
This one?
What? No, I meant like the standard one, right?
Okay, that's fine. Open system settings.
Well, yeah, I'll have to allow it, right? Otherwise, it won't let you share.
Is it working now?
Sometimes with Zoom, you may need to exit and re-enter. So, but try to share, and if it doesn't work, then you can exit and re-enter.
Oh yeah,
now
it seems like now the desktop view is actually the one that you're sharing there.
You have a new laptop, or this?
Yeah.
Or you updated the operating system?
And I eternally have problems with computers. I'm much older than you think.
This is not coming.
I think if you move this one to there,
What?
like yeah, so
Or if you go into
screen.
presentation mode,
So
command.
what should I say?
Option
What should I do?
I think just go into presentation mode here and in your keynote.
No, presentation mode, and I just
Command Option D.
Yeah, that did the trick.
guys, and just like that, right?
Yeah, I don't know how we're going to gauge the standard because
We don't need that, right?
I think maybe
Do we need it? We don't need it, right?
that's right.
No.
Okay.
No, for you they need it. Once in the back, I want to hear it.
Okay, I mute myself for a second.
This is the mic for the questions afterwards. Right?
Okay.
Yeah, you have to turn it on using the button.
Yeah.
Is this correct like this? No.
I think the other one.
No, why?
Now you look like a pilot.
Like this?
Yeah,
It's already fine.
No, it's work. It works.
Is this?
Yeah.
But it's on my nose.
Yeah.
Which way is it, guys? Which way?
It's on the right side.
Aha, so that was wrong.
I don't think there's. You can probably even bend it the way. I've seen a lot of people having it on the other side.
Yeah, but it's twisted the other way around.
But I'm lost. I don't know how to.
For as long as it doesn't bother you.
It does bother me actually.
You can also not if you want to speak out.
Wie geht das denn?
The other side.
Nach links?
It's weird.
That's the best you can get.
Yeah, okay. Should I unmute myself?
Yes.
Test.
Thanks guys for coming for the first session in the afternoon. So my name is Narin, and I'm going to be sharing the first two talks. First talk is by Ronnie Tumale from Würzburg on nonlinear protective electric circuits.
Okay, thank you for showing up, and let me thank Monica, Odette, and the other organizers for having me at this workshop. It's been quite interesting for me in particular, because it's typically quite an orthogonal crowd that I typically don't meet at conferences. So it has been particularly inspiring to me. The latter fact is also the reason why I added a perspective to the title, because I want to make it more look like a survey-ish presentation, such that we have several points of triggering discussion amongst each other on the topic. And the topic is specifically nonlinear Floquet circuits, but in a way also topoelectric circuits from a broader perspective, because I'm pretty sure many of you have never heard of the field. And so I would like to spend some time to get you accustomed to it. So with this, does it work? No. Okay, so let's start with the beginning of the field. And I'll be quick because this is fairly standard by now, how the field developed. It all started with Haldane and Ragu, and essentially, I think this field of topological metamaterials is very anachronistic in the sense that it started to develop in quantum systems and only later migrated into classical systems. Typically, it's the other way around, like magnetism or a related phenomena in condensed matter. And that paper was pivotal. And you can see, I also always like it when I see it, because you see the duration of the submission. It took like 3 years something until it eventually got published. So it was submitted in March 2005. And Srinivas Raghu is a professor at Stanford now. He gave me all the communication with the referees, because I just wanted to see this as a document, as a historical document of how this came about. So that happens when, like Duncan Haldane, you're a little bit too much ahead of your time. So topological phases in general have proliferated, and they did so in very different fields. Let me be very short on this. There are countless systems, and most relevant to this audience, all sorts of optical systems, including really inspiring platforms like ultra-cold atomic gases, which allow to combine topology and quantum physics. But before I move on to more related fields, let me just start with the topoelectrical circuits, and more specifically with our work. I should say that I would say the initial work was done by David Schuster and Jonathan Simon in experiment, and Leonid Glasman in theory in 2015. This was a pair of papers that appeared, but for some reason, the community hadn't really picked up on it in the first 2 years after submission. So when we started, there weren't that many other follow-up papers on that around. And we realized fairly quickly, for us at least, that this is a really new arena to do physics. And let me give you a short core idea of what we do. And it's not entirely connected to what you see on the slide, because given it's a survey talk, I always try to slightly go through the slides with a little bit more abstract perspective. The thing that you want to appreciate in order to see topologic circuits is a true change in the conception of topological bands. When people typically talk about topological bands, it's an energy to momentum map. You associate energy with momentum. The first core thing you have to appreciate is that when I talk about a band structure of a circuit network, I'm not talking about an energy, I'm talking about an admittance. So the admittance is the inverse complex resistance or impedance, and it allows for a wonderful, convenient measurability. So essentially all you do is you thread currents, and then you measure voltage against ground. It's literally a high school level experiments at their original conception, but it gets more complicated later. And as always, when people try to establish a new platform for topology, probably the simplest one is obviously the Suschil-Verheger model. And you have heard this too much. Let me just focus on the thing that you might find funny. So you can map the Suschil-Verheger model to just an alternating sequence of capacitors of two different capacitances. And there's a little bit more subtlety in there if you want to see the first work I ever did on circuits was for a class, and I wanted to solve the Suschil-Verheger model. And when I wrote down the matrix, I noticed there were just -1s and 1s. So I felt there must be a pi shift should do it to get the Suschil-Verheger. And then inductors and capacitors have a pi shift in their impedance. So that was the start of the field for me. And the reason why I'm showing you this is the role of the inductors in this really prototypical model we started off from. What these inductors do is they serve as an effective Fermi level to the bands, because you can shift the admittance of the bands by varying the inductor here, because you're connecting the sequence of capacitors to ground. And by the way, you connect them to ground, all you do is you adjust the admittance levels. So obviously you will tune them such that the topologically interesting levels will locate at zero admittance, such that they would show up in experiment as a peak in the impedance. That is basically the game, the name of the game, so to speak. And we did a little bit more sophistication for our first experiment. and by the way, if I sound a little bit too excited about it, I'm a theorist, so doing an experiment for me was a big thing. So the first experiment we did was we took two switches that were synchronized. They either turn to the right or to the left. And when you look at this structure here, these switches, they interpolate the Suchré-Verheger model between T and 1 over T. Why do they do this? If they turn to the left, then the chain of capacitors starts with a large capacitor. And when they turn to the right, the chain of capacitors starts with a small capacitor. So it's a map of T to 1 over T. And logically speaking, one of them, if T is unequal to 1, should be in the topological regime of the SSH model. And the other one should be in the non-topological regime. I actually soldered the first thing together with my students. And that was the result. So we could not only measure the eigenstate of the Suchré-Verheger boundary mode, but by log-ins, we could measure the impedance and the phase. And the phase was needed to get the eigenstate. So it matched. And that what you see to the left was the first original data we took. And just to get the idea straight, when there are the topological zero modes, it means zero admittance modes. That means large impedance. So when these modes are there, our measurement would yield high impedances. And when they are not there, our measurement would yield small impedances. From a viewpoint of an electrical engineer, it is quite estranging how changing the boundary condition of an, if you wish, infinite chain of alternating capacitors changes the impedance so much, right? But we understand why that is, because the existence or non-existence of these zero modes. And as you can see, it's a logarithmic scale. So the impedance changes by more than 4 orders of magnitude, just by that switch, just by varying the boundary condition of the SIP. Now, this was 2017, and I will wrap up the past 7 years by giving you a 5-minute summary of all the fields that have now been investigated through triboelectric circuits. It has been proliferating quite a bit in terms of experimental groups because of the low entrance threshold. It literally takes you $5,000 or $10,000 to get the right log-ins, and then you can start measuring, actually. So let me start anachronistically with something that people like. Let's talk about an electric topological insulator. That's, again, Haldane is with you when you work on topology in many ways. So I wanted to implement this lattice quantum Hall effect model proposed by Haldane in 1987. And so we did. That was a work which we called, obviously, the Haldane circuit. And what you see at the lower equation is the circuit Laplacian. The Laplacian is a mathematical object. If you wish, it's like a kinetic theory for arbitrary objects. In mathematics, the Laplacian can take a very general shape. You can assign a Laplacian to a chessboard. You can assign a Laplacian to a discrete lattice. You can apply a Laplacian to a network. And that's what we have here. What we used were certain circuit components that electrical engineers would know, but maybe you wouldn't. So for instance, a negative impedance converter through current inversion, what this guy does is it gives us the Faraday effect that basically allows us to reach the topological regime of the Haldane model. And in case you don't see the Haldane model, you know that you can move the circuit connections around. So if you talk to an electrician, they will always make 90-degree angles, but you can deform it, and then it actually takes the form of the Haldane model the way you would know it from the original paper. So let me show you the experiments we did. I told you that the way we connect the circuit network to ground allows us to shift the admittance bands. So I give you 3 examples. One is where I shift the level into the valence band, and I adopt Conant's meta theory language, but you know what I mean. So I'm at the left side of that slide, and the green little point here below denotes where we inject the current into the circuit. So here we inject the current at the boundary, but we are at a level where we are deep in the valence band. So what happens is the signal gets scattered all over the 2D circuit, right? In the second experiment, we place ourselves in between the valence band and the conduction band, but we thread the current in the center of the circuit. what we would expect is it's gapped, so it should just decay very quickly. There's always dissipative environment, so that's exactly what happens. However, and I now cut out a little piece of the circuit board on the right side. If I now place myself in between the valence admittance band and the conduction admittance band, and I thread a current pulse into the system, it does what you have seen from papers like Mohammed Hafezi, Moti Segev, and many others. It shows the propagating, in this case, voltage mode, which, by the way, has a lot of appreciable features. First of all, it doesn't decay as quickly. Like the dissipation can be controlled much more conveniently than many other photonic platforms. And second, you will see how incredibly versatile the platform is. Let me show you. I will shift a little, as I show you, I give you an anachronistic survey. This was only done last year, but I think it's important for you to appreciate what circuits can do. I was amazed by the progress that magnetic field realizations in ultra-cold atomic gases have achieved in the past years. And what I like to tell, in particular, this subpart of the audience here is that in circuits now, we developed a component that basically allows you to assign any phase of whatever you like to any connection. Like e to the I phi can be completely modeled at your liking. And the way we accomplish this is a little bit difficult. I don't have much time to go into this, but what I want to tell you is the toolbox for circuits and building U1 gauge theories is basically complete. And it costs 5,000 euros and it is very cheap to assemble. So in that sense, it might be exciting to do testing or other things at the circuit level before one would proliferate it to more involved, more challenging platforms. With this ahead, let me also say that circuits are, of course, quick. If a theoretical proposal comes around, we can build an experiment sometime. Well, experiment, I mean, it's very close to the simulation itself, but the circuit experiment can be done in 2 months. And that's happened for the multipolar topological insulators, or higher order, you might also call them. Multipolar, I call them because you can recast them as a bariflux dipole and multipole. That's why I call them multipolar topological insulators, but it goes back to the science paper 2017, made quite a splash back then. And nowadays it's been pursued also in quantum materials, but we wrote down the first experiment showing that in an unambiguous fashion. There were contemporaneous waveguide proposals as well. And that's so much for that. We can easily move on to any topological band structure you can think of. Let me shortly show you topological semimetals. Obviously, we started with a graphene band structure, and I don't have time, but maybe you're interested in this, so I shortly mention, you should notice that electronic circuits are networks and no lattices. So they are graphs. Mathematically, a graph and a lattice is very different because there's no length scale associated with a graph, right? You just have transition elements and there's no length scale. So that means that a brick wall lattice and a honeycomb lattice are truly equivalent. So the lattice becomes a gauge degree of freedom of the graph theory. That's actually fun to see. So when you move from a lattice theory to a graph theory, the lattice becomes a gauge if the connectivity, if the adjacency is preserved. Okay, the circuits are not constrained to any dimensionality. You can actually go to 5 dimensions, 6 dimensions, whatever you want. You just have to fix the connectivity. You have to fix the adjacency matrix. The first thing that was done then were wild circuits, but this proliferated. Let me show you one really exciting thing that has happened in the past 2 years, and maybe that's also interesting for other platforms. That's why I'm bringing it up. That's hyperbolic space. I don't have time, but when you do the Beltrami-Poincaré projection of hyperbolic space, really it looks like a fractalish thing, but then all the connections should have the same strength. Yeah, but here you see how a graph is an advantage to realize such a thing, because the distance doesn't correlate with the connectivity that you implement in the adjacency matrix. So we could easily build hyperbolic lattices with circuits. And that, I think, is the most beautiful slide I have to offer on this. It shows half how the circuit board looked that we eventually had soldered. now then we stopped doing it. And we just measured, we measured the Euclidean drum versus the hyperbolic drum. And you look at the different vibration modes in the sequence of the vibration spectrum, depending on the negative curvature of space. This got lately, this got into a truly interesting direction. And already yesterday evening, we had a lot of interesting conversations with Odette and Said on what these circuits can really do and what they cannot do. Like superficially, if I just take a bunch of circuit components and maybe I have, say, 100 circuit nodes, obviously there's nothing that the computer couldn't simulate that these experiments could ever do. However, there's this one big thing that I believe technologically will be the key gate for the field to proliferate, namely the highly integrated circuits. Highly integrated circuits, you know how transistors got shrunk to billions now in your cell phone. So when I want to proliferate a lattice and I want to have a lattice made of capacitors, which is huge, I can actually do this with highly integrated circuitry. Now, why would I be interested in this? We just published in PRL a proposal how to map ADS-CFT onto a circuit. And the reason is quite simple. You have a certain type of compactified hyperbolic space representation that would allow two universes that intersect through a black hole horizon. And that sounds like science fiction, but it's very simple in circuits. Basically, now we need a program and a protocol to carry over these small node circuit proposals we have into highly integrated circuits. But I just sketch it here and move on. So why I even talk to you about circuits is that I believe it has a lot of transition potential into the platforms you're interested in, be it ultra-cold gases maybe, or other photonic platforms. And I just want to sketch one or two successes we had in the past years to do so. The first thing is that you would know this PT symmetry, which was quite in the news in the 90s and so on, and still is heavily researched in the context of photonics. And there is a PT symmetric thing. You would know about PT symmetry. Maybe you would also know about anti-PT symmetry. Anti-PT symmetry also exists, but the point had been in photonic systems before we entered the field with circuits, you could never get to a sufficient signal to noise ratio in photonic crystals. And the reason is this: when they build PT symmetry, they don't build honest PT symmetry, which is to say they have a decaying envelope times PT symmetry. So they vary large loss, small loss, large loss, small loss. So if you do if you decouple it, it looks like a PT symmetric system modulo an overarching dissipative envelope. With electric circuits and operational amplifiers, you can perfectly tune the gain at your liking. You have as much control over the gain as you have over the loss. And we could perfectly tune PT symmetry, and as such reach the first regime of anti-PT symmetry. Okay, we did a lot of non-Hermitian skin effect. We had the first experiment on non-Hermitian skin effect, but I won't get into this. That was a paper from 2020. And with Alex Samite, we also used these circuits as a starting point to investigate an optical fiber realization of non-emission skin effect that would serve as a topological light funnel. That again was in 2020. So we're still 4 years ahead. We're still 4 years past from the presence. Now let me shortly approach the main topic of the talk. And I'm sorry that I don't assign as much time, but I feel it's more appropriate in case you've never heard of circuits. I think it's more rewarding for you to hear the broader scope of it. Nonlinear circuits obviously is the thing to go, because in circuits, I claim there's no other platform that as conveniently allows you to tune nonlinearity versus linear terms as circuits. You can tune it exactly as you want. You can endeavor any parametric angle of your differential equation at your liking. And the first project we did on this was, again, who would have guessed, a nonlinear SSH model. And together with Johan Dunkel from MIT, and what we studied was how nonlinearity affects the bulk of a topological phase versus the edge modes of a topological phase. And what we witnessed is that the orbits of the edge are sort of insensitive to the imposed nonlinearity, while the bulk immediately responds to the nonlinearity. We can talk about all this in more detail during the conference. I would be glad to talk more about it to you, I know. So the next thing we did was a senoidal nonlinear topological SSH. The reason why I'm bringing this up is really because it's really a fantastic realization of the Korteweg-de-Vries equation. And you would not believe how simple it was with circuits. We just had to pick, there's big electrical engineer books of all the circuit components that exist. And so you have to just look what you take. And what proved very successful were varicap diodes. So we just used varicap diodes and built it and followed up on a theoretical proposal by Motohiko Ezawa and immediately measured it. Finally, we also did, so that got mixed up here. Sorry for that. Yeah. So let's go to Floquet circuits. And as a precursor, let's talk about the Fowler's pump circuit. That's not really Floquet, everyone knows, right? Because it's just, you just carry it with the potential. It's not really Floquet. But I would say it's fair to call it a precursor. That was work done with Lavio Preti, who's in the audience. There we could see that actually the broadening of a voltage pulse signal can be enormously reduced by transporting it through the circuit via a Fowler's pump. So the broadening gets really suppressed. So it might actually be interesting for signal procession because you don't have a broadening of the signal at all. That was quite interesting. And most lately, we looked at a Floquet SSH model. But here, and I told you before, like we can go to any system you like, but we always start with the SSH, but we certainly not stop at that. And what I really like to emphasize here is when people talk about Floquet, you basically think of it as a lattice built in frequency space. What I always found troubling is how do you create a boundary in frequency space where you would see the nucleation of topological edge modes. There has been one paper by, I keep forgetting the guy's name in Stanford. Yes, Xianghui Fan, on a related proposal in one of his preferred realizations. But this is pretty much the second way of doing it. And what we are doing is we are using, so we have a Floquet drive, which again is super simple in circuits. Imagine for a second what you need. You need a time varying resistor. You might need a time varying capacitor or a time varying inductor. This all exists and can be bought super cheap, super precise. You can even buy time varying diodes and immediately connect nonlinearity with Floquet, right? So it's a very natural thing to grow into. And so in this particular case, we used time-dependent capacitors. And the thing that's on the archive already, but it has only been recently posted 1 or 2 months ago. And what we find is, of course, at some point, we cut off our frequency lattice in Floquet space. So we have a cutoff here, so we have to keep that in mind. In the upper plot, you see green-shaped states, purple-shaped states, and yellow-shaped states. And to the left, you see the real part and the imaginary part of the impedance value, which is just the spectrum of the circuit Laplacian. And one case in the trivial regime of the Floquet SSH model and in the topological regime. And what you can see is the onset, and I have to stop there, is the onset of topological boundary modes nucleating at a boundary in frequency space, which we could conveniently create in circuits. So I believe this will give birth to a lot of interesting considerations of Floquet topological phases, because now we don't have to resort just to space-time topological invariance, like understanding the bulk. We can now also understand the surface modes of a Floquet topological phase. So I believe this can be quite impactful for the future. As a general, let me just repeat, to me, I believe electric matter in that sense is still largely terra incognita. Basically, aside from interactions, let me put it like this, aside from contact interactions, basically the degree of tunability is, I believe, unmatched, and it's super simple, super accessible, and it could be an incubator for interesting ideas in other platforms. And so let me thank my team and my collaborators and you for your attention.
Thanks for the nice talk. Several questions.
Yes, thank you. Very nice. So you mentioned rocks. What are the limitations of the rock origin?
The limitation, whatever you can solder, really. I mean, you have to make it. You see, when you send in to companies and they get you the circuit board back, there are templates where you fill in how the different circuit components have to be connected. That's how you grow a circuit board, right? And there's honestly, as soon as anything you can recast as an adjacency matrix, you can build in a circuit. Could you say that again? Yeah, that's another big advantage of circuits. I mean, connectivities can always be drawn between circuit nodes, like the non-locality is built into this graph structure. For instance, you can easily interpolate between open boundary conditions and periodic boundary conditions, like on a computer, you know, you take two final nodes and they are either connected or not, right? And the reason is that these circuits operate in the microwave regime, so they are slow, they are super slow. So that means that the spatial distance, if I have two circuit nodes connected like this, and two circuit nodes connected like that. You're right, there should be spatial differences, so that should sort of enter. But in large orders of magnitude, that doesn't make a difference in circuits because the frequency scale at which the voltage pulses propagate is so much slower that the time difference in the electron traveling from here to here, is a negligible component, which is why the non-locality is very much built in the structure. Any coupling you like, yeah. Okay, maybe you're referring to parasitic resistances of larger wiring. This has to be accounted for. Yeah. Oh, that's not what I'm saying. We can intentionally pick who is connected with whom and with which strength, because the circuits components specify the connections. Yeah, I'm not sure I fully understand the question. So when I buy 10 unlimited ones, anything you can buy. You go to the Target store when you're in the US, you go to the Target store and say, what kind of capacitors do you have?
Maybe have a small discussion with the brain, like any other questions?
About the ASCP correspondence and elaborate maybe, first of all, what will you measure? Are you measure current correlation function in the bottom? The second question is, should I be surprised about the fact that you establish ASCP correspondence in a linear system?
I think, Jonathan, at the end, it's a huge leap now, and I don't know whether it will work, but I'm currently trying to get a highly integrated representation of this with millions of capacitors. So I need to reach a certain amount of complexity simply to get there. That's the first thing. The simulations are exactly as you say. We calculate the CFT correlators, bulk surface, 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 bulk, bulk, and you can match them onto what you would expect from an ADS CFT correspondence. The point you're bringing up is at the heart of the whole thing, and I'm not even a strong proponent of ADS CFT for that reason, because I'm still unsure about it. The ADS CFT community makes a statement that in an effectively non-interacting gravitational theory, you can get in a higher dimensional, effectively non-interacting gravitational theory, you can match correlators with highly correlated quantum correlators at the surface, which is to say at lower dimensions. I really want to put it to a test, but when you do it with finite size simulations, actually, you know that the finite size threshold will not allow you to unambiguously get there so far. So I believe it's the best case for these circuits as a system per se, because we will need to transcend what you can model on a computer. And you can only do this by an assembled type 2 hyperbolic Poincare projected lattice of 1 million capacitors or something. And only then I could give you an answer.
Any final questions? Maybe I have one quick question. So you mentioned that you want to combine the nonlinearity with the Fouquet.
Yeah.
The Fouquet's theorem is for linear systems.
Yeah, sure. So, okay. Okay, so the Fouquet operators, there are some papers on addressing how Fouquet could be generalized to nonlinear systems. And the current project we're working on, but we haven't come far enough yet, is how to basically combine the two experiments I just showed you before. So we use varicap diodes that are time-driven. And actually what we're doing right now, we are trying to investigate to which extent Fouquet theory prevails in the presence of nonlinearity. And we are investigating whether there can be a topological state of matter which is only stabilized from nonlinearity. And that combined, to us at least, I'm not sufficiently educated in this field, but to us it sounds quite new. And we are still exploring the very first data we have on it.
Thank you. That's the
No, they're not at all.
So now you join. You probably want to make yourself visible just in case.
Should I keep the sound?
Yeah, the sound you should keep because otherwise they can't hear you.
Okay.
And there has to be a connector somewhere. Is there a connector? No. HDMI to use the yeah, the adapter. Yes, yes. Yeah, like this. So I'm going to try to make like a sound when we have like something like 5 minutes or so. And, all right, are we all set with online? Hopefully, are we all set online? Yes, we are. Okay. All right, so that's. All right.
Does it work? Can you hear me?
Okay, so next up is going to be by Kseniia Vodenkova on continuous coherent control feedback with time delays.
Yeah, so my name is Kseniia Vodenkova. I work with Hannes Pichler in Innsbruck, and today I will talk about continuous coherent quantum feedback and will present our tensor network solution for it. So let's just talk a little bit about why it's actually interesting to look at time delays and at the feedback. So let's start with the most simple paradigmatic model of an atom in front of a mirror. So we have an atom that coupled to one-dimensional waveguide that is terminated on one side by a mirror. Now, if the time required for the photons to propagate from the atom to the mirror and come back again to the atom is negligible, we are in so-called Markovian regime, so our environment doesn't have memory. And this is quite easy to solve. It's possible to solve essentially analytically. Now, situation becomes more interesting if we are dealing with the significant time delay. That is that the time delay is much larger than the intrinsic timescales of the atom. And then we have non-Markovian problem, which is much harder to solve. And it's also interesting from the standpoint of what kind of states you can obtain with such a setup. So let's look at it as a quantum circuit. We have our atom that interacts with the left and right propagating modes of the waveguide, and essentially entangles them as the time propagates. And as a result, we can, for example, it was shown that we can obtain, for example, 2D cluster state, which is a state that is suitable for universal measurement-based quantum computing. And also, this kind of setups already were realized, for example, using superconducting quantum circuits. So it's quite an interesting field of research. But as a theoretician, my question was, can we simulate the dynamics of the atom in such setups? And specifically, there were particular goals in front of us. So we want to have a driven nonlinear system. We want to go in the limit of long time delays. And that actually allows us, due to constant pumping, to have unlimited number of excitation in our delay line. And we want to be able to simulate not only transient dynamics, but also steady state, reach the steady state. And up until now, there were no theoretical methods that were answering all these challenges with the numerically exact solution. So this is our big goals. And now I just want to talk a little bit more about what we're actually dealing with, what is the model. And I will talk only about the simplest setup, but that can be generalized. So again, simplest setup, atom in front of a mirror, and our total Hamiltonian is the sum of the system Hamiltonian, that's the atom, the Bath Hamiltonian of the waveguide, and their interaction. So for the system, we can take, again, the simplest example is coherently driven two-level system. Now the Bath Hamiltonian is also quite simple. So here's the waveguide with the mirror, and we're dealing with linear dispersion in the waveguide. And now their interaction. So we have our atom coupled to left and right propagating modes with the coupling rate gamma. And you can see these two types of interactions in the Hamiltonian. Now, I just want to maybe look at this interaction Hamiltonian from a little bit different perspective. And for that, we first officially introduce now the delay time, which is twice the distance between the atom and the mirror divided by the group velocity in the waveguide, and the phase phi, which is the phase that the photon acquires when it propagates to the mirror and comes back to the atom. And another thing what we're going to do is that we go from frequency modes description to time modes description. It's quite easy to understand. Let's look at the picture of our waveguide. So it's a little bit adjusted. We essentially have, again, our left-right propagating modes. And now we divide our waveguide in this time modes. That is, our time modes, as time propagates, they are moving according to the arrows that are depicted here. And the labeling, the time labeling, basically just tells you after which time this specific mode will interact with the atom. And you can see again that there are two time modes with which our atom interacts at one specific instant. Again, those are left and right propagating modes. And thus we can rewrite our Hamiltonian, and you can see this two time modes, and the difference between them is exactly the delay time tau. Okay, so now I will actually tell you spoiler. And I will tell you how we're going to solve this problem without diving in a lot of details, but it's a spoiler. Okay, so here's the trick. We're going to map our non-Markovian single node problem with just one atom to Markovian many-body problem. And specifically, this is a cascaded 1D chain. What is a cascaded interaction? So let's look at the example of just two atoms. When the output of the first atom becomes the input of the second atom, we're dealing with this cascaded interaction. And nice thing about it, we can write master equation. And here there are two first terms in the master equation, which are just local terms for each atom, 1 and 2. And then the last term in the parentheses, this is the interaction, this unidirectional cascaded interaction between them. And just to simplify a little bit for you, let's just call this cascaded Lindbladian, okay? We just know that there is a master equation, a nice Lindbladian. Now, 1D cascaded chain is a chain of such atoms, every two of the atoms in which interact through this cascaded coupling. And again, we can write our master equation as a sum of this cascaded interaction between neighboring atoms. And now I will just explain a little bit how it is actually, how can it be connected to our original problem of just one atom in front of a mirror. Well, what happens, you can think that the atom sends information about itself to, again, itself at a later time. So the information will come back after this delay time tau. And then the process continues. So it's kind of a letter in the future for the atom, letter to itself. And this is exactly our 1D cascaded chain. It just consists of these replicas of the original atom at different times. And the difference between them is exactly delay time tau. But again, I'm a theoretician, so I cannot just tell you, oh, this is the spoiler, that's it. I have to actually figure out what's going on. And for that, we were diving into tensor network framework. And I hope experimentalists will be still with me. And I will be able to maybe explain what's happening here for everybody. Okay, so what we're going to do, we're going to characterize our evolution. So we have little time steps, how our total setup evolves. And correspondingly, we have this, now our time modes become so-called time beams. So these are little boxes. At each time step, they're moving according like a conveyor belt, again, according to the arrows. And each this small time beam, this little box that is represented here by a white blob, can have only 1 or 0 photons, just because they're quite small. At each instant, our atom interacts with the 2 time bits, and they are labeled by the number of time steps you need to go in evolution for this time beam to interact with the atom. Okay, So now we can try to solve the Schrödinger's equation for the whole system. And each time step of this evolution, according to the Schrödinger equation, will have the following form. So it's a tensor, this UI, and it has 6 legs. So we have the system input. This is basically how our atom looked before the time step. Then we have the input, right moving input and left moving input. These are the states of our time bins before this time step of evolution. And correspondingly, we have 3 outputs for each of the state. And now we want to build a tensor network using these little blocks of evolution. And we say, okay, we have our atom initially in some state psi. And we also say that we assume that right moving input is just always vacuum input. And I'm not going to put it on the scheme to just make it simpler. But again, it can be generalized to different states at the input. All right, so we take the initial state, we apply the first tensor, first step of evolution. We continue, and that happens until we reach specifically time tau, the delay time. And now here's the trick. You can see that after this time, the time bins that were right moving output, they become the left moving input right after this delay time tau, which is k time steps. And that's why we need to connect corresponding legs. And here is what we are doing. We're connecting output left, output right moving to left moving input. And then we keep going with our tensor network until we build it up for some time Tn we are interested in. And it's a 2D tensor network, and they're usually hard to contract. Moreover, we actually want to look at the dynamics of the atom itself, right? So for that, we need to consider the reduced density matrix of the atom. So I take the tensor network corresponding to the wave function and another one, and I make a sandwich. So this is our density matrix, right? 2 wave functions together. And then I also trace out all the bath degrees of freedom, and these are our light blue legs. You can see they're traced out, and the only thing that is left is this dark blue leg at the end. This will give us the state of the atom at our time Tn. And now a little bit of magic, because I don't have time to tell you everything, and I also, I guess, need to convince you to read my paper after the talk. So we actually managed to look at this tensor network and rigorously prove that the transfer operator, this blue box, the transfer operator of this tensor network, is exactly the one-time step operator, evolution operator of 1D cascaded chain I was talking about before. And the rest is what we're going to do with this nice operator we obtained. Well, we're going to use matrix product techniques to deal with it. For those who are not familiar with the matrix product techniques, let me just say that for many body system, we can introduce a matrix for each side, and then the connection between the matrices, that is the size of the matrices, will tell you essentially how the sides are correlated. Okay, so what we're doing here, we just evolve the operator. We take this transfer operator, we evolve this transfer operator, we start from identity operator, we evolve, and we obtain the total evolution operator for 1D cascaded chain at some time tau, right? It was our delay time in the matrix product form. And then the last thing that we need to do, essentially, we just need to contract it, so-called shifted periodic boundary conditions. So this snake-like contraction here, we just restore the connection between the system legs, right? There was atomic legs. So we just reconstruct it. And this way we restore the original tensor network and now can see what's the state of the atom at specific time. But now you can ask me like, okay, you did this strange matrix form thing, but is it efficient? Like, what's the difference? Was a huge 2D tensor network, maybe it's still very hard to calculate. And for that, I have a slide on the computational cost. Well, it happens that we can observe so-called entanglement entropy area law. So essentially, the entropy tells you how the different sides in this matrix form are correlated. And if the total length of the chain becomes bigger, you can actually see that the entropy doesn't grow. So we have our chain length M here, and you see the plateau of the entropy. So at some point, the correlations between sides stop growing. There is no more correlation. And these are very good news for us because this means that we can simulate this operator for 1D cascaded chain very efficiently. And this is a numerically exact and efficient method in the end. And now just to show, okay, we have a method, what can we calculate with it? Well, we can calculate the population evolution up until some very long time for different driving strengths. We can also actually target directly the steady state for the atom. And we can also deal with more complicated systems, like many node setups. And our method also works for it, and it's also efficient. And then another thing that we can also do is that we can obtain certain properties of the output field. So that's the field that is leaving our feedback loop and never coming back. And we can calculate the output spectrum and multi-time correlation functions, still using the same method. And I believe I have a few minutes still, and I can, 5, okay. I think it's perfect. That's just the last cherry on top of this work. It's mean field approximation because, okay, so we had this sophisticated tensor network matrix product method, but can we do something simpler for example, experimentalists to calculate things easily, fast, like even faster than what we do? And our answer is yes, there is a regime in terms of driving omega of our system and delay time tau. And in this regime, we observe very small entropy, the entanglement entropy, which means the correlations are very small. And we wonder, maybe in this regime, we can actually approximate our operator for cascaded chain as a product operator. And we use mean field approximation for that. So essentially, we just look at one atom at one replica in our cascaded chain and treat everything else as a field. And it turns out that, yes, in this regime, you can actually see that the fidelity of the mean field approximation with the exact solution is pretty good. Moreover, the mean field approximation also can explain and show certain behavior of the output field properties, like here it is spectrum. So this is also a very nice addition of this method, I would say. And now I'm coming to outlook. Just to summarize, so we have the systems with the coherent quantum delayed feedback, and we came up with a solution for it. And this solution is efficient and doesn't scale exponentially with the delay time or the total time of the evolution. And now what we want to do, we actually want to break it. We want to ask ourselves the question, can we find a regime of such setups where our method won't work, where the scaling will be bad? What can we do? What can we add to the setup to break it? Maybe it's nonlinear dispersion. Maybe it's a specific driving that we can do. Why we ask ourselves this question? Because we are interested if we can obtain interesting and complicated correlated states, for example, states with polynomially decaying correlations as the output states of this setup. And we are also interested if we can add other types of non-Markovianity to our method. And then last thing that we're also interested in is realization, even though, of course, there are some already realizations. It's always interesting to see if it's possible to realize such setups in different platforms. So if there are ideas, I'm very happy to hear that. And with that, I want to come to the end of the presentation. If you're interested in this work, please see our paper, which will soon appear in PRX. And thank you for your attention. And I also wanted to thank my rabbits for their support.
Thank you so much. So I think we touched upon this a little bit, but it's about the scaling with both dimensions. So usually when we use CBD or PDE element to simulate in time as a network, then time grows with time. So you have to somehow you have to truncate their both dimensions. This is a truncation, it's an approximation, we also have the total error. So in your case, how do you cope with this, with the entanglement growing over time? Do you target your cascaded chain in some way, or how are you able to do this in general?
Thank you for the question. I think it's true that I maybe not explain it in detail. So the total time of the evolution and what we are worried with this entanglement growth actually doesn't happen in our case. So the number of sites in our chain, right, corresponds to the total time of the evolution, because each next replica is after times tau. Therefore, more we have replicas, more time, for longer time, we evolve our system. And it happens that with the chain growth, our entanglement stops growing at some point. So we are not dealing with we don't have to deal with that. Exactly. That's why it's efficient.
The same of your system grows with time, and you have two figures in network, so there is no kind of
Can you say it again?
So you have to deal with a lot of subtractions at each time step, and the number of contractions will grow if you calculate a circle, because the depends on that one figure.
Yes, we do contraction. There is trotter, there is as with the we cut the singular values, but the point is it's controlled, right? Because moreover, we can see that let's just say numbers that for the plots that they showed in the presentation to obtain the precision 10 to the power of -10, we needed, in many cases, bond dimension 20, which is very small. So you can always check how much you cut. And the efficiency of the method comes with the fact that you need very small bond dimension, and it actually stops growing at some point. And you still get the same small error. But we can also talk about it later.
Let's talk. My question is related to the nuclear approximation. So you sort of see by analyzing where this area works well. Do you have any physical intuition on why it's below?
Yes, we actually do physical intuition. Though first it was analysis, and then we tried to explain it. So essentially, that's the regime where we have strong driving, so constant laser pump, and we have long time delays. And essentially what happens that the atom sends information, and then when this photon with this information goes in this feedback loop, the atom will change a lot. And when the photon comes back, it's essentially doesn't change much the evolution of the atom. So basically, what happens is that, okay, after one feedback loop, there is still some effect. But after the second time, it's already not relevant. So for different regimes, we might still see like a few feedback loops, or many actually of them still having like the photons coming back and having the effect. But in this specific regime, there's just after the second round trip, it's already, the photon doesn't bring much change. Oh, that was but we can talk a little bit about it later if it's interesting.